Hey there, ladies and gentlemen. Let's look at some direct variation. Today, when we talk about direct variation, that means something varies directly with something else. So that's like saying, a good example of a direct variation is baking. If you make one batch of cookies and you need a half a cup of sugar, if you make 2 batches, you're going to need a whole cup, and 3 batches will be 1.5, and so on and so forth. So the idea here is that, like baking, the ratio has to stay the same. So in this case, we're talking about if the ratio of the 2 variables is constant. Then the variables have a specific relationship known as what we already brought up, direct variation, meaning they vary directly with each other. So basically, we're looking at this equation here. Remember, y equals kx. The k is slope. So really, it's y equals mx that we're talking about. It's just when it's a direct variation, for some reason they call it a constant, and they use the letter k instead of c, which they love to confuse, but k is the constant of variation, or slope. So we say often that y varies directly with x. So that means, like I showed you at the beginning when we're talking about the sugar, or baking, in other words, it's going to vary directly. As the x changes, the y is going to change by the same amount each time as well. We could also say y is in a proportional relationship, it's very special, with x. All right, this is a great example of a direct variation. So let's see what this looks like. So you're babysitting, you get paid $7 an hour. So if you don't babysit, you're not going to make any money. You babysit for 1 hour, you make $7. You babysit for 2 hours, you make $14. 3 hours, $21, and then 4 hours, $28. So as you can see here, the relationship between the hours you babysit and the amount of money you earn is changing directly. So if you notice, it starts with 0, 0, which is important, and it grew by $7 per hour, right? So that would be your rate. The next thing is y per x constant. So what we're going to look at is the y over x. So let's say, I don't know, I'm going to say 7 over 1, and I simplify, that gives me 7. 14 over 2 gives me 7. I can continue this pattern. 21 over 3 simplifies to 7, and so on and so forth. So when we look at this equation we've just created is y equals, the rate at which it's changing is 7, so it would be 7x. So if this is your table, your equation is y equals 7x. Essentially, what we need to check is whether or not you can multiply across the table. So basically, I'm looking this direction. 0 times 7 is 0. 1 times 7 is 7. 2 times 7 is 14. 3 times 7 is 21. 4 times 7 is 28, and so on and so forth. So we can say, yes, we can multiply across the table. And we multiply by 7 each time. So now let's look at a non-example. You're renting tents for your birthday party in your backyard, and there's a delivery fee of $30, and then you're charged $10 an hour. So let's start with this first one. So you order the tent, the guy shows up, and you realize, you know what? I'm not going to celebrate my birthday this year, so I don't want the tent. But the homie says, I'm sorry, you still owe me $30. So it's still going to cost you $30, even though you didn't keep it at all. Then you're like, okay, well, maybe I'll have it for an hour. And so then you're at $40, then $50, $60, and then $70. And the way we came up with this is it's $30 and then $10 per hour. In this case, it didn't start at 0, it started at 0.30 because even though you didn't rent it, you still had to pay that delivery fee. Now, when we talk about what it grew by each time, it grew by 10 each time, but it did not start at 0. So let's look at this. If I do 30 over 0, that doesn't even make sense, does it? Let's say if I do 40 over 1, nope. What about 50 over 2? If I simplify that, that's 25 over 1. So none of this is working out. None of that gives me what I need. I'm showing that those are not equal to each other. But we can write an equation from this. The equation we can write is y equals 10x plus 30, which is how we found these values over here. So it's pretty clear here that this is not a direct variation for a bunch of different reasons. It doesn't start at 0, 0. The ratio or the proportion, it's not proportional, and our equation doesn't quite look right. This little piece right here, this right here makes it not a direct variation, just because of that. So in this case, we're going to ask ourselves that same question. Can you multiply across the table? When I multiply this way, well, 0 times nothing will give me 30. This is times 40, times 25, times 20, times, I don't know, something else. If this is not consistent, then it does not work. So again, we need to be able to multiply by the same value each time. That constant value has to be multiplied every time in order for this to be a direct variation. So in this case, they're telling us that we have a proportional relationship. And just to kind of refresh your memory, a proportion looks something like this. A over B equals C over D. Just to kind of give you an example. They must be equal to each other. So in other words, it's one simplified fraction of the other. Or multiplied, depending on how you look at it. So I'm actually going to set up my proportion here. I'm going to set this guy up as a proportion. So this would be 7 over 10 equals. And over here, I have m and 18. So I'm going to set that up as m over 18. Remember, there are different ways you could set up proportional relationships. So in this case, I can use cross product. Remember, that's when you multiply. You probably remember it being called bat and ball or some version of that. But we would multiply 18 times 7, which would give us 126, and then divide by 10. So that would be 12.6. So that means this value right here is 12.6. So what you should be able to see here is, if I made this into a decimal, this would be 0.7. If I did 12.6 divided by 18, I also get 0.7. So that means this is a proportional relationship because they would simplify to the exact same thing. So the missing side length that we were looking for is 12.6. Of course, there's no units of measure, so then we can just leave it at 12.6. All right, here's another situation we have. So using scale drawings is a lot like a direct variation because you should know that the ratio remains the same. So if we're using the equation y equals kx, they're telling us that the ratio is 1 to 400. So in this case, we want to know how long the model should be. So that means we're taking the proportion and we're setting this up. 1 over 400 equals, and of course 400 is the actual, so then we would put 1320 down here, which is where that comes from there. And so we're trying to find this. So if I multiply 1320 times 1 and then divide by 400, I get that x equals 3.3. So if I take 3.3 and divide by 1320, I get, as a decimal, it's kind of ugly, but 0.0025, which is the same as this fraction over here, 0.0025. I know that's kind of outlandish and kind of crazy to think, but it helps us to find the missing length if we know that there are proportional relationships between different items. So if I were to write an equation using this, I would say y equals 1/400th x, because that is our constant of variation. So let's say, this one was about 1300. Well, I'm assuming that I have y equals 1 over 400 times x. And let's say that my bridge is a different bridge, different model. I don't know, what was the one over? Let's say this one is 2100, making it up. So if I take that and I multiply it, or those two values, the model would be 5.25, I guess inches, we'll go with inches, 5.25 inches. So that's how knowing a relationship is proportional can come in handy, because then you can use that rate or that constant rate to find your equation, and then you can continue from there.